Alright, so welcome back to particle physics and the Standard Model. This is lecture 51, and in the previous class we saw how to generalize our formula for the scattering cross section, in particular the differential scattering cross section, to the optically thin limit, right, where you do not expect many scatters between the beam and the target. So, you have to think about measuring the probability of the scattering of the incident particle on the target, right. So, this in particular applies for particle on particle scattering. Okay, there is no real beam to think of and there is no real target to think of, sorry, there is no real beam at least to think about. If you have just two particle scattering, then this is how you would generalize. You would think of this in terms of the probability for scattering. Now, having written down the differential cross section this way, we took a little digression to note that that gives rise to the notion of the integrated luminosity in a collider setup, which will basically tell you how many events that you can actually measure in some differential way if you want, right, in a particular solid angle or in a particular energy bin and so on. Okay. So, that came from the notion of luminosity. The luminosity is a fancy name for just the flux of the beam, alright. So, you integrate the flux over the time of the running of the beam, that gives you the integrated luminosity, which is a measure of how much data you have to work with, alright. And then we came back to 2 to 2 scattering and tried to derive a general expression using QFT notions. So, first we rewrote the flux as the relative velocity of the two particles that we are thinking of divided by the volume over which the scattering is happening, and we spent some time working out what this probability is. The probability comes from the transition amplitude, right, squared of course, and then we have to take the correct norm and multiply by the correct phase space. Yes. So, the norm we obtained as basically 2E1V times 2E2V for the initial state, and similarly 2E3V, 2E4V for the final state. The phase space was nothing but counting the number of cells that you have in this phase space of the final state, right. You need, if you do not have enough phase space to go into the final state, then the scattering is not going to happen, right. Everything has to work out that way. So, that is nothing but the volume times the actual volume times the volume of the Brillouin zone you are thinking of in momentum space divided by 2 pi cubed for each state. So, the total phase space is the product of these two double volumes. Okay. So, that is where we were last time. Now, we are going to put all this together back into the expression for the cross section in order to derive our master formula for the cross section for 2 to 2 scattering. Okay. So, that is where we are headed, and when we to get there, I am going to introduce yet another little notion, okay, which is the matrix element in QFT. Okay. Matrix element could mean anything, but let us see what it means in this context. See, all of the transition is captured in this transition amplitude, right. Without, if this t is 0, everything is 0 here. You need to transition from some initial state to final state, right. That is what the S matrix tells you, correct. Now, one way to write this is, okay, let me actually, I have jumped the gun a bit. So, the transition amplitude, one way to write this is to factorize out quantities like these, okay. The 2 pi 4th accounts for some phase space, and then I know that I have to conserve for momentum in the process. So, I am pulling out a delta power 4, okay, with the sum of the momenta basically. So, P1 plus P2 minus P3 plus minus P4 or plus P3 plus P4 depending on the convention, the sign that you give to the final states. I am just summing them all up and taking a delta function for that. Basically energy momentum conservation. Once I do that, I can now pull out, I will take out one more I and write a real number. Okay. So that M, okay, is related to the matrix element. How is that? Because now I can write the actual transition amplitude. What I first wrote was a transfer matrix, right? That would be still this and still this. Now I pulled out the I, so I am left with some matrix element that takes the initial state to the final state, right? And that matrix element is what we call the matrix element. In quantum field theory. Okay. So this is the quantity that we'll keep seeing again and again. All right. That's where all the juice is. So remember when we did Feynman diagrams, I said that at the end of the day, the Feynman diagrams helped us to get the amplitude. What I meant was it helped us to get this matrix element at the end of the day. Okay, once you have that, you have the actual transition amplitude and hence the cross section. Okay. So using that, I'm going to make that visible, that equation. This implies that if I were to take the absolute value squared, because that is what I am going to plug into the cross section at the end of the day, right. What is that? That is nothing but S itself, right. The identity matrix is not going to do anything, right, that just goes to 0. So when I write S as identity plus IT over here, if I take the inner product of F and I, that's just 0, there is no transition there, alright. So that is what this is. Now I am going to write this thing again as delta 4. Okay, I am going to write it slightly strangely. I will explain why I write it this way. So I write delta power 4 of 0, then there is a 2 pi to the 4th, but now I am squaring, so 2 pi power 8. Then this whole thing I am just going to call that M now, okay, or M squared, okay. So I am going to annotate this a bit now, so it is not confusing later. This thing is nothing but that, and this thing we got by already enforcing already one delta condition enforced. Okay, I am just getting momentum conservation twice. So if I am already enforcing it in the integration at the end of the day, that just goes to 0 anyway. We know that anyway. So that becomes 0. Okay. Okay, let's slightly simplify that. This is still that. Now what is delta power 4 0? Remember delta power cube 0 was what? The volume, right? Volume over 2 pi cubed. So wouldn't that also mean that if I have delta power 4 of 0, we are talking about 4 dimensions now, so it is the volume times time divided by 2 pi power 4. Yeah, that is all it means, right. So that is what I am going to write down here. It is just volume times time. Now there is a 2 pi power 4 in the denominator, that cancels a 2 pi power 4 in the numerator, so that I just have 2 pi power 4 left from that 8 M squared. Okay. Okay. So what do we have now? We have a dp, we have the denominator terms, we have the numerator term, we have the phase space, and we have the rest v and t and v1 minus v2. All of this we have, right? So we're going to put all that together. Let's do it again bit by bit. Putting them together. First, let me write just dp, right? That is going to be t over v 1 over 2e1 2e2, okay, m squared times d cubed p3 over 2 e3 2 pi cubed. This comes from the phase space part, right? So we actually had 2e1 2e2 2e3 2e4. I am going to push the e3 e4 terms into the phase space bit. Okay, so remember in the phase space bit we had this dqp over 2 pi cubed. I am just going to push the E3 and D4 from the inner products into this. Okay. So we have D3 to the 4 over again, so 2E4 2 pi cubed, and the rest of the terms go for a ride. So I'll just write that down. Okay. Now this is a special form of writing this probability because I have now separated out terms, okay, that happen to be actually Lorentz invariant. Do you remember when, again go back to the lectures on Klein-Gordon equation and all that, when we wrote down the solutions, do you remember I said having a term like this, right? This is a Lorentz invariant measure, I said. Remember? And then I asked you to go derive it, which is not that hard. You can also follow Srednicki to see how this comes about, right? So look at this. So this is Lorentz invariant, this is Lorentz invariant, this is also Lorentz invariant, right? It's after all a condition, it's just a delta function condition, right? Said differently, I have basically separated out some Lorentz invariant parts which involve some phase space, right? So this part is called, at least in Srednicki, this is what it's called. This is called D-lips, just stands for Lorentz invariant phase space. Okay. So if you can identify the Lorentz invariant phase space in these problems, then the rest of the terms you can easily put in. Okay. It's worth writing it down. Lorentz invariant phase space, not any phase space. Okay. Okay. So we are almost done. So now I just have to write with this. What is now the cross section? We had dp over t v v1 minus v2, right? But now there is a t in the numerator that cancels the other t, correct? And that would mean I am now left with m squared, which is always there. The cross section is proportional to the amplitude squared. That is what we are seeing here, the absolute value of the amplitude squared. Maybe if I had mentioned m was a real number before, I am wrong. Okay, I actually I just isolate the I out of it. M could be a complex number also, but it's just a dimensionless number. That's the main point. The 2e1 goes for a ride, 2e2 goes for a ride, and crucially we have a relative velocity in the denominator. Okay, cross section intrinsically contains a relative velocity in the denominator because that accounts for the flux. The slower the particles move towards each other, the larger the cross section, the more time they spend with each other, right. That is what this captures, multiplied by d ellipse. Okay, that is our master equation for scattering, for 2 to 2 scattering. Okay. Now this can be easily extended to 2 to n scattering. How? Just identify d ellipse correctly, suitably. So all that means is now you will put, if suppose there is a third particle, you will put it d cube p5, right, and then you have to be a little more careful about the 2 pi factors and so on. And down here the initial state you still have only 2 particles, it is just 2e1, 2e2. Okay, if it is 3 to 2, then things are a little more different. That is even harder to imagine what is going on there. It is not even clear what we mean by a flux there. So that is a harder thing to work out, but it can be worked out. Okay. Now here's, I am going to introduce one more term here. It is worth knowing this term so that you can separate out some physics parts, okay, in your head. This m squared bit, right, this is what encodes the dynamics in the problem, and then the rest of the terms encode the kinematics of the problem. So what do I mean by this? So when we say kinematics, we are talking about energies and momenta and velocities and so on, okay, and conservation of these in certain contexts, etc., etc. Okay. And when we say dynamics in particle physics, we mean in particular, the structure of the interaction itself. Ultimately this can be traced back to the Lagrangian, that is given to you inherently in nature. That is what is going to set the transition amplitude and ultimately the cross section also, right. Whereas the kinematics is the kinematics, throw any 2 particles, you have to conserve energy and momentum and so on. Okay. So this is a useful way to separate out the 2 moving parts that make up the cross section. Okay. Now once we have the master formula, we can immediately implement this for one interesting configuration, which we will take up in a later lecture, but it is worth immediately implementing this and finding an expression, a simplified expression for one particular configuration. What could that configuration be? It's 2 to 2 scattering in the center of mass frame or center of momentum frame actually. Okay. Because this happens all the time, right. At the LHC, the lab frame is the center of momentum frame, correct. So at the LEP also this was true, turned out to be very important, right. What does that mean? It just means P1 equals minus P2, and necessarily that means P3 is minus P4. Okay. And I can define, because they are the same in magnitude, I can define some final state momentum that I am going to call Pf, nothing but the magnitude of this final state momentum for each particle. Okay. Yet another thing we can write down is because it's a center of momentum frame. What is E1 plus E2? This is always true. E1 plus E2 is E3 plus E4. But in the center of momentum frame, we saw that this was exactly what the center of momentum energy was, right? If I were to take the invariant mass squared, this is what I'll take as the center of momentum energy squared in the expression, right? Okay, so that's what this is. So these variables help us to simplify the expression up here in the master equation. Now in particular, I can now write out what this Lorentz invariant phase space should be. Turns out that is, see, in the Lorentz invariant phase space, look at d ellipse, look at the expression down here for d ellipse. I have an integral over momenta, right, with a delta function, and then I have all these factors of 2 pi cubed in the denominator, right. So let's count this a bit. So I have basically 2 cube, that gives me 8, and then pi power 6 I have in the denominator, right. But in the numerator, so sorry, 2 cube gives me 64. Now in the numerator I have 16 pi squared, right. So all that put together will give me 1 over 16 pi squared, correct. So that much I have. On top of that, I can pull out an angular integral, and I am left with the integration over 1 momentum out here, okay. And then I still have the E3, E4 in the denominator. What I have done is integrated over this. So there is a P3 and a P4, right. Let's say I have integrated over P4, okay, and then I got rid of 3 of the delta functions. So I am still left with 1 delta function. That is nothing but conservation of energy, okay. So let me just write it down. What we have done here is integrated over P4 and got rid of delta cube of the 3 momenta, sum of the 3 momenta, okay. And then you might wonder what happened to other factors of 2 here. So we had a 4 and all that, right, down here. So that again, you just have to so when you work this out, you will find, so in the angular integral I have other factors of 2 pi and all that, right, 4 pi and all that. So all those things get cancelled, and as you work it out carefully, you will find that indeed this is the final expression, okay. So the factors of 2 and other things, I will leave it to you, okay. Now again, to simplify this further, okay, let's switch variables a little bit. This thing, right, let me call that some z. You will see in a moment why I am doing this. Otherwise this integral is very hard to calculate, right. I have a PF here. There is a relation between PF and E3 and E4, but it is not very obvious what that is. But if we were to go to this new variable, I can now write what is E3? It is just P3 squared, which is PF squared, plus M3 squared under square root, right. Similarly E4 is the same thing with 3 replaced by 4 in the mass, right. So then you will agree with me that this implies dz over dpf is, what happens if I differentiate? I have a 2pf divided by 2 times the square root of this, right? That's nothing but Pf divided by E3 plus Pf divided by E4. That's it, right? Of course, I can simplify this a little bit more. If I cross multiply, I get E3 plus E4 in the numerator. So that's nothing but ECM. I still have the PF, and downstairs I have E3, E4. So I'm just changing variables from PF to DZ. Okay, that would mean d ellipse is d omega over 16 pi squared. Now I have a dz integral. Okay, PF I can keep for now. It is implicitly a function of z, that we know now, right? And the delta is a delta of z now. But the important thing is the limits have changed, right? I need to make sure that my center of mass energy is larger than m3 plus m4, right? So I need to start with, so if basically what I'm doing is, if I set Pf to 0, that's barely producing the particle. You just produce the particle at rest. So if I set Pf to 0, what happens to the z? The lower mass, the lower end of z, the lower limit, that's basically m3 plus m4 minus ECM, right? That's what I've written down here. Of course, it can go all the way to infinity, right? So you can have infinite momentum also. Okay. So what is this? If you do the evaluation, what is an integral over a delta function written this way? That is nothing but d omega over 16 pi squared. Now I can happily pull out the PF over ECM, because that's not what I'm doing the integration over. I just have a heavy side theta function that ensures that the initial center of mass energy that I pump in is larger than the sum of the final state masses. Okay. So that's one bit, and I'm also going to use the fact that V1 minus V2 can be expressed as this. So this is a very trivial thing to derive. I'm going to ask you to do it. Okay, where the initial momentum is what I define as, P1 and P2 are equal, right? The magnitudes. That's what I mean by Pi here. Okay, I mean this is very simple. Okay, it's very simple to derive. So you can get that, so that I can put all of this together now to go back here and write the differential cross section, okay, in the center of momentum frame. That maybe I'll write it in a different color again. No, first I'll write it in blue. So that would be d sigma. See, I have a d omega out here, right? I can now think of a differential cross section with respect to the solid angle, okay, in the center of momentum frame. That is 64 pi squared E squared in the center of momentum frame again, okay. I have a PF in the numerator and a PI in the denominator. Of course, I have an m squared, right? So all that still goes along for a ride, right? And finally, that theta function. Okay. So, ECM minus M3 minus M4, which ensures again that you have enough energy in the initial state to form the final state. Okay. So, this is a general equation for the differential cross section in the center of momentum frame. Okay. Now, let us take one special case, a fun case, which is if the masses are equal. So, I will write this down and then wrap up the lecture. Okay. If the masses are equal, it just means what? The initial momentum is the same as the final momentum now. Correct? So, let us call the masses m. Okay. So, that simplifies to the center of momentum cross section is now 1 over again 64 pi squared ECM squared, just m squared. I can of course put the theta function, making sure that ECM is larger than 2m. Okay. So, this we will make use of in a couple of lectures to do a very fun calculation of a scattering process without actually using QFT. Okay. But see, all the right ingredients are here again. Okay. If I increase the center of mass energy, that means the cross section is falling, and of course, it has to depend on m square. So, all the ingredients are right here, and it looks like now it looks like a simplified expression, right. All right. So, in the next class we will deal with decay rates, which is an extension of the notion of cross sections. So, see you then. Thanks.